Hello and welcome to another online lesson for A-Level Physics. This is the second lesson in the waves topic, and the learning intention for today is to understand the principle of superposition. What I would like you to do is think back to GCSE physics now for a few moments and decide whether the following waves are longitudinal or transverse, and they are radio waves, sound waves, primary seismic waves and secondary seismic waves. Pause the video and write down your answers, please. So, radio waves, like all electromagnetic waves, are transverse waves, which means, of course, that they oscillate perpendicularly to the direction of energy transfer. Sound waves, on the other hand, are longitudinal waves, which means the oscillations in those are parallel to the direction of energy transfer. Now, seismic waves can be split up into two categories, P waves and S waves. You will remember, if you did triple physics, that a P wave is longitudinal, whereas an S wave is a transverse wave. The success criteria for today's lesson is to recall the principle of superposition, to describe the difference between a progressive wave and a stationary wave, and to explain how a standing wave forms. Now let's start off by considering what happens when two waves meet with each other. We can see that happening in the animation below. When two waves meet, they pass through each other. At the point where they meet, they will combine for an instant and then move apart again. That is called superposition. Now, the principle of superposition states that when two waves meet, the total displacement at a point is equal to the sum of the individual displacements at that point. Now, we have here on the board a diagram that shows this taking place in action. This is a cross-sectional view of what we would call noise-cancelling earphones. Now, the purpose of noise-cancelling earphones, if you've never used them, is basically to block out any background noise that is around you. They're particularly successful at doing this when the noise is constant. For example, if you sat next to a machine or on an aeroplane, they would produce like a constant buzzing kind of noise. Now, the way that works is that inside the earphone there is actually a very small microphone which detects the background noise. Now, you can see there on the diagram that blue wave, the incoming background noise is being detected by the microphone that is inside that earpiece. That noise is picked up by the microphone and sent to noise cancellation circuitry, which essentially inverts the wave, which means swaps it round. And it then sends it back to the headphone. The original background noise and then the newly added waveform will then cancel each other out by interfering destructively with each other because of superposition. So as you can see there on that fourth note, so to speak, the red line and the blue line are perfect opposites to each other. They've been inverted. So when they superpose, because the total displacement is equal to the individual displacements at that instant, the constant sound that will be produced there will be zero. So the only sound that will get through the earphone will be the sound from the device that it is plugged into. Now let's consider what a stationary wave is. So a lot of musical instruments work using stationary waves. For example, if you watch a guitar string get plucked by a plectrum or something, that produces a standing wave. Now, a stationary wave is formed when two waves of the same wavelength and frequency that are travelling in opposite directions pass through each other. When the two waves pass through each other, superposition will take place. Along the stationary wave, we will get nodes and antinodes getting made. A node is formed where the two waves will interfere destructively with each other and cancel out, whereas an antinode is formed where the waves will interfere constructively with each other and reinforce each other. Now, it's important to note that in a standing wave or a stationary wave, energy is not transferred along them like they are in progressive waves. Now here we've got three stationary waves shown in these diagrams, okay? And there are slight differences between the two of them, but the way they will be formed is exactly like what we said on the previous slide. So if we take that top one as an example, if we plucked the centre of the string, then obviously we would create that standing wave shown there. Now each one of those strings are in what we call a different harmonic. So a stretched string can vibrate in any of those ways. The top string is vibrating at its first harmonic and it has a node at each end. A node, of course, is a point of no vibration, and it has an antinode in its centre where we have the maximum displacement of the wave. If the frequency of the waves along the string is increased, because bear in mind these are being formed by waves travelling in opposite directions, if we increase the frequency of those waves, then we can move to the second harmonic, which is the second diagram shown there. That has got three nodes. It has a node at each end as well as a node in the centre. And then the bottom diagram there, that will be the third harmonic. And what you can see there is that we actually now have four nodes. We have a node at each end, and we have a node a third of the way along and 2/3 of the way along. And of course, you can also see that there are three antinodes in that third harmonic as well. Now there is an equation for working out what the frequency of the first harmonic of a wave on a string is going to be, and it's given by the following equation, which is that the frequency of the first harmonic is equal to 1 divided by 2 multiplied by the vibrating length of the string multiplied by the square root of the tension in the string divided by the mass per unit length of the string. Now, of course, if we change the length of the string or alter the tension in the string, then that means that the frequency of the standing wave will be changed in accordance with that equation. You do need to know, though, that that equation is what would give us the frequency of the first harmonic. The frequency of the second harmonic will be double that frequency. The frequency of the third harmonic will be 3 times f. Now let's have a look at an example question. A vibrating string of length 60.0 centimetres has a mass per unit length of 1.12 times 10 to the power of minus 3 kilograms per metre. Calculate the frequency of the first harmonic note when a tension of 12.5 newtons is applied to the string. So the equation that we need to use for this is the equation for the fundamental frequency, or in other words the frequency of the first harmonic, which is shown there. That will be the starting point to answer this question, writing down the equation. Now we need to substitute in the values for this. The length of the string should be given in metres, so we will convert 60.0 centimetres into 0.6 metres. The tension in the string is 12.5, and of course the mass per unit length, which is mu, is 1.12 times 10 to the minus 3. So we can substitute all of those values in, as shown there, and then when we put this into the calculator, we should get an answer of 88 Hz as being the frequency of the first harmonic. Example 2. A string which has a vibrating length of 0.66 metres between two fixed positions vibrates at a frequency of 220 Hz. The total length of the string is 0.91 metres and the total mass of the string is 3.1 grams. Show by calculation that the tension in the string when it is sounding the harmonic shown is about 70 newtons. So what we need to acknowledge first of all that is the harmonic shown there is not the fundamental frequency or the first harmonic. Indeed, what is showing here is the second harmonic, and we will need that to be considered. With it sounding the second harmonic then at a frequency of 220 Hz, we want to work out what the frequency of the first harmonic is. So the frequency of the first harmonic will be half the frequency of the second harmonic, which means that the frequency of the first harmonic will be 110 Hz. Now that we know that, if we want to use the equation for the first harmonic, we'll also need a value for the mass per unit length of that string. The mass per unit length of the string will come out as being the mass, which is 3.1 grams, so convert that to kilograms, divided by the total length of the string, which was 0.91 meters, will give us a mass per unit length of 0.00341 kilograms per meter. With that in mind, it's now possible to rearrange the equation for the fundamental frequency, or the frequency of the first harmonic. Because we're after the tension, the starting point of the rearrangement will be to multiply by 2 times L, which will give 2LF equals the square root of T over mu. If we then square both sides of that equation and then times by mu, what we will end up with is that the tension is equal to 4F squared L squared mu, as shown here. Now we simply substitute the values into the equation, and you must show that step because this is a show that question. So we would do 4 multiplied by 110 squared. Remember that we do need it to be 110 because F is the frequency of the first harmonic, 220 is the frequency of the second harmonic. Times that by 0.66 squared, times that by 0.00341 to give us an answer of 72 newtons, which is of course approximately equal to 70 newtons as we were asked to get to. Now let's have a go at a task. So I'd like to read through the task and then press play once you've completed it to check your work. 2 progressive waves, P and Q, are travelling towards each other on the same stretched string. At a certain instant, the positions of waves P and Q are shown. The first question is to state the condition for waves P and Q to form a stationary wave. Well, one of the conditions was given to us in the question, that they need to be travelling towards each other or in opposite directions. The other conditions that need to be met are that those waves need to be travelling at the same speed, have the same wavelength and have the same frequency as each other. Okay, so that's the answer to the first bit. The second question is to draw on the graph paper the appearance of the standing wave that will be produced at this instant. Now, bearing in mind, of course, that the principle of superposition tells us that the displacement is equal to the sum of the individual displacements. So, if I take the highlighter, just to make my point, the laser pointer, here we go. At this point here, we've got a maximum negative displacement that's 1 square negative. At the same point here, the displacement is positive 1 square. So that means that the total displacement overall will be 0 at this instant. Then again, if we just pick another point here, we can see when this is a 0 displacement here, we have 0 displacement here. We have a displacement there of +1. Here we have a displacement of -1. So we can see that we've got perfect cancellation taking place at the instant shown. So what we would draw for the resultant wave here, the standing wave, would just be a flat line because you've got perfect destructive interference taking place. We were then asked to label any antinodes with a letter A. Now remember, an antinode is a place where you will have maximum displacement happen. Now at the moment, the displacement across the entire wave is 0. But as those waves continue to travel, because we've produced a stationary wave, we will have antinodes form and then they'll collapse back down, form again, collapse back down and so on. We need to know where those antinodes are going to form. Now, if we look at the waves, say, let's take this first point here. As this wave moves along, here is going to end up being a positive displacement again, because as this wave continues to move, you can see that this line will continue to climb, and here we would have a maximum displacement. Likewise, as this one moves in the opposite direction, there will end up being a maximum displacement here as well. So that means that on this point here, we will have an antinode formed. So if I go to the, if I click us on, you can see there that here we would actually get an antinode forming. Now at this point here, we have perfect cancellation taking place. So that means that this will always be a node. But then if I look here, this point here, again, as this continues to move and this wave continues to move here, we'll have another antinode taking place there. A node would exist at this point, and then an antinode would exist here, and so on and so forth, so that these antinodes form where we will end up having positive displacements meet on one wave, meet a positive displacement on another wave. Because clearly at this first point here, you will have a positive displacement of that wave meet a positive displacement of this wave here. Likewise, if we just pick another point, let's say this one here, as this moves along here, you've got this maximum displacement here as this moves along, meets this maximum displacement here at that point. So that is where we would draw those antinodes. Now then, we can also get stationary waves produced in pipes as well. We've looked at them on strings so far, but we can also get stationary waves made in pipes. The sound in a pipe is capable of forming a standing wave, and that is the basis of which many musical instruments work, things like flutes and recorders. When a stationary wave is created in a pipe, a node is created at a closed end, but we have an antinode made at an open end. So what you can see here is then, with that in mind, the first harmonic will be a quarter of a wavelength in a pipe. The second harmonic will be 3/4 of a wavelength, and the third harmonic will be 5/4 of a wavelength. So in other words, a wavelength and a quarter. Now we're going to have a go at some summary questions. When the question appears on the screen, please pause it, watch through, answer the questions, and then press play to check your working out, folks. Question 1 for the consolidation questions. A piano is a musical instrument that works using vibrating strings. The wave along the string is a transverse wave. What is a transverse wave for 1 mark? Well, the answer to that is that a transverse wave oscillates perpendicular to the direction of energy transfer. Part B. The sound wave produced is a longitudinal wave. What is a longitudinal wave? Well, a longitudinal wave is a wave that oscillates parallel to the direction of energy transfer. And then the last question asks for the definition of ductile. A ductile material is one that can deform plastically before it fractures. That, of course, links back to the materials topic. Question 2. The diagram shows 2 progressive waves on a string travelling towards each other. Part A is give the definition of a progressive wave for 2 marks. We went over that definition in the previous lesson. A progressive wave is one that transfers energy from one point to another without transferring any material or causing any permanent displacement of the medium. Part B. Which of these diagrams shows the shape of the string after the waves have passed through each other? Well, we know that superposition is going to occur when they do pass over each other, and they'll actually destructively interfere with each other to give a flat line. So at the instant that they do touch those 2 waves, you'd end up with part A. However, it was after they've passed through each other. Now, after they've passed through each other, they just continue on as normal. So in other words, this negative wave here will continue along, this positive wave here will continue along. So the correct option is option C. Standard demand. The diagram shows 2 ways in which a wave can travel along a slinky. State and explain which of these waves is longitudinal out of wave A and B. Well, the one that's longitudinal is going to be wave B. We can tell that it's wave B because the spring will have to oscillate parallel to the direction that the wave travels or transfers energy, and we can also clearly identify that's longitudinal because it's made up of areas of compression and rarefaction. Then on part B, it says, on wave B, indicate the wavelength. So a wavelength on a longitudinal wave is the distance between the centre of one compression and the centre of another compression, which I've labelled for you there. And then part C says, on the diagram, use arrows to show the direction in which the points P and Q are about to move as each wave moves to the right. So if wave A is moving to the right, then we would expect the peak of this wave to continue to move to the right. The material, though, isn't being displaced in itself, so we will need this peak here to end up being here. For that to be the case, point P is going to have to move upwards in order for this antinode to continue to move along this progressive wave. So the answer there for P is that P is going to move upwards. If wave B is also moving to the right, then this compression needs to start to move to the right, which means the compression may end up here. So if we need the compression to be here instead of here, this particle is going to need to move to the left in order for the compression to become here. So that particle is going to move to the left. Question 2. Describe how a stationary wave is formed on a stretched string. So this is only 2 marks, but it can be asked for more. But just to get 2 marks, we would say a wave is reflected at one end of a string, and then the reflected wave will interfere and superpose with the incident wave. There'd be no harm, however, in giving extra details for pointing out that where the 2 waves interfere constructively, we get an antinode. That would also definitely be worth mentioning if it was worth more marks. Question 3. A piano string has a tension of 681 newtons. It vibrates with its first harmonic with a frequency of 92.5 Hz, and it has a mass per unit length of 1.87 times 10 to the minus 2 kilograms per metre. Calculate the length of the string for 3 marks. So we use the equation for the frequency of the first harmonic, but we need to rearrange this equation to work out the length of the string. So we multiply up by L to give us F times L equals a half root T over mu, and then we divide by F to give us L equals 1 over 2F root T over mu. We then substitute values in, so we have 1 over 2 times by the frequency is 92.5, that's the frequency of the first harmonic, times by the square root of the tension, which is 681, divided by the mass per unit length, which is 1.87 times 10 to the minus 2. And all of that on the calculator should come out as 1.03 metres. Part B says the diagram shows a string stretched between fixed ends. Copy the diagram into your book and then draw onto the diagram the second harmonic mode of vibration. Well, remember that a second harmonic needs to have 2 antinodes in it, so the shape would look as so, where you've got a node at the centre, nodes at the end, and you've got those 2 antinodes in there as well. Now let's have a look at some stretch and challenge questions. This is question 1. A piano repairer replaces the wire that produces the highest note on a piano. The wire has a vibrating length of 0.050 metres. He uses a wire that has the following properties. Its diameter is 3.5 times 10 to the minus 4 metres. Its density is 7.8 times 10 to the 3 kilograms per metre cubed, and the breaking stress of the wire is 3 times 10 to the power of 9 newtons per square metre. We want to calculate the tension required for the vibrating wire to produce its correct frequency of 4.1 kilohertz. We'll assume that it's producing that in its first harmonic. So the equation that we need to use is 1 over 2L root T over mu, and we need to rearrange that for the tension. So to do that, we times by 2L to give 2LF equals root T over mu. Then we need to square that. To square 2LF gives us 4L squared F squared, and then we multiply up by mu to put a mu on the end. We now need to substitute values in. The length was given to us in the question as 0.05, so that's not a problem. The frequency is 4.1 times 10 to the 3 hertz, because obviously we'd want it in hertz, not kilohertz. But the value of mu has not been given in the question. I do not know what the mass per unit length of the wire is yet. So I will try and work it out. Mass per unit length means that mu is going to be mass divided by length. I don't know the mass of wire either, but I know that the density of the wire will be its mass divided by volume. So I can say that the mass of the wire will be the density of the wire times by the volume. Now I don't know the volume of the wire either, but if I combine those two equations, M is equal to density times volume, so mu was mass over length is now density times volume over length. Now of course you know that if you do area times length, that gives you volume, so volume divided by length is area. So we can say that the mass per unit length is equal to the density times by the cross-sectional area. Remember that area is pi times diameter squared divided by 4. So we can therefore work out what the mass per unit length is. So to work out the mass per unit length, we will do pi times by 3.5 times 10 to the minus 4 squared divided by 4 will give us a mass per unit length of 9.6 times 10 to the minus 8. We can then substitute that into the equation for tension by doing 4 times by 0.05 squared times by 4,100 squared times 0.7 times 7.8 times 10 to the power of 3 squared times by the cross-sectional area should give us an answer of 126.2 newtons. Now for part B, we want to evaluate whether this wire is safe to use. To evaluate whether the wire is safe to use, we need to consider what the breaking stress is. The breaking stress is 3 times 10 to the 9. So we need to see if the stress in the wire is actually going to be as much as the breaking stress would be. So stress we know is force divided by area. So in fact what we could do is work out what the breaking force would be to provide that breaking stress. So the breaking force will be the stress times by the area. The area of course we worked out previously. We worked it out to be equal to 9.6 times 10 to the minus 8. But of course you can just do pi d squared over 4 instead. That gives us a force of 289 newtons, so we can say that it is safe to use the wire because we only need 126 newtons to reach the required frequency. Let's have a look at the second question on stretch and challenge, which says that the diagram shows an arrangement used by a student to investigate vibrations in a stretched nylon string. This is actually one of the required practicals on A-level physics. We haven't done it yet, but we will be doing a video that goes over this required practical. The student measured how the frequency of the first harmonic vibration of the string varies with the length of the string, and the results are shown in that table. We've got 3 values for length, which give us 3 values for the frequency of the first harmonic. We want to show that the data in that table is consistent with the relationship frequency is proportional to 1 over length, or in other words, the frequency is inversely proportional to the length. If that is the case, then that means that the frequency would actually be equal to a constant multiplied by 1 over the length, because we can remember from GCSE maths, to eliminate a proportionality sign we multiply by a constant. So if that is true, that means of course that frequency times length will always give the same constant value. So if I multiply each of those length values by the corresponding frequency, we should get the same answer. Now we actually get 81.5, 81.6 and 81.2, but they are approximately the same. Bear in mind this is experimental data and they are close enough to say that yes, that does show that frequency is inversely proportional to length. With it being a show that question, you would be expected to show that for all three pieces of data. Part B says the string used by the student has a density of 1,150 kilograms per metre cubed and a uniform diameter of 5 times 10 to the minus 4 metres. Determine the tension in the string. Well, we start off again using the equation for the first harmonic, which is F equals 1 over 2L root to T over mu. But I don't have a value of mu, so I need to find out what mu is before I can put numbers into that equation. Mu, of course, is the mass per unit length. Now, I don't know what the mass of the wire is, but I do know its density and I do know its diameter. So I can make use of the fact then that mass is density times volume to work out then that mu would actually be density times by area, because of course volume divided by length is area. That means that when we do this calculation, we would do 1,150 multiplied by the area of the wire. The area of the wire can be found by doing pi times by 5 times 10 to the minus 4 squared divided by 4, which gives an area of 1.96 times 10 to the minus 7. And so therefore we end up with a mass per unit length of 2.258 times 10 to the minus 4 kilograms per metre. Now that I know all the values I need, I rearrange the equation for the first harmonic to give me the tension equals 4 F squared L squared mu, and it's simply a case of substituting numbers in now. So I do 4 multiplied by, well, we've got multiple values for F and L. It shouldn't matter which one we pick. I'm going to pick I'll pick the bottom row, I think, to do 4 times 116 squared times by 0.7 squared, because that's the corresponding length, times by the mass per unit length, which gives a tension of about 6 newtons.